Hello, today we're going to be running through our 4 technologies related to optical profiling. So we'll have confocal, focus variation, interferometry, and on this machine behind me we've got the capability to measure thin film thicknesses. So the machine that I'm stood next to is a Sensofar S neox, and using this equipment type we're able to flip between those 4 technologies to be able to measure all different types of samples. So first we're going to take a look at interferometry techniques. So what we're going to do is run through a breakdown of the different technologies and the reasons as to why we would use them. We'll go into the 3 measurement techniques that we have for interferometry, and then we're going to run through a measure sample and show you how it's done basically. So the first thing I'm going to do is refer to the technical summary from Sensofar. So on this technical summary, we're going to be focusing on the right-hand side. So you can see that the interferometry setup on the Sensofar is perfect for measuring smooth samples, microscale features, nanoscale features, and some thickness measurements. So when we talk about the different types of microscale and nanoscale features, this could be step heights, it could be smooth polished finishes. When we're referring to the consumer electronics industry, the automotive industry, they're looking at high surface roughnesses. And when I say high, I mean low on the nanoscale side of things. So when we go on to the specifics now of these surfaces, so we can see that the interferometry setup has a nanometer system noise. So no matter the objective, whether that's a 10x, a 50x, we have the same system noise on those objectives. The PSI setup has a 0.01 nanometer system noise, which is incredible when you're talking about roughness measurement. And we can also measure thicknesses from the ranges of 1.5 microns to 100 microns. So when we are to talk about some of the limitations related to interferometry, the reason that the Sensofar system has the confocal and the focus variation is for specific types of samples, so that we can cover a much broader range of applications. And when we look at slope limitations, we don't see the same slope acceptance when we're to look at focus variation and confocal. So that's why we have the ability to change between those techniques. So the last thing I'm going to show you is the 3 different types of technologies that we have on the Sensofar for the interferometer. So we have CSI, so this is the most versatile mode. We've got a 1 nanometer height resolution at any of the magnifications. We've got PSI, so PSI is the phase shifting interferometry. So this is where we're looking at super smooth surface finishes. So the example being the component that I have on the machine here, which is a gold sample. It's got a very high nanometer level roughness, but it's also got some surface scratches on. So we could potentially have used PSI to measure that sample. The problem with this sample is that there's these surface scratches. So what I'm going to do is I'm going to use the ePSI, which is the optimized CSI for smooth roughness surfaces. Okay. So what this does is it combines the CSI and PSI measurements to create our surface. So now what we're going to do is we're going to go to the Sensofar software, and you can see that I've got the component set up, and as I roll through here you can see that we've got the surface scratches that I was referring to earlier on. So what I'm going to do is I'm just going to move to my reference position. I'm going to scan 5 microns positive, 7 microns down, and a total range of 12 microns. So within that 12 micron span, we're taking 167 steps, so that's planes on the surface, and we've created our data set. So from here, we've got our all of these small surface scratches. So if I was to zoom in on a couple of them, so we can see on the edge here, we've got some of the deeper surface scratches. And using the mouse here, I can over-exaggerate the error. So you can see we've got some particles. This could be dust, etc. on the component. So if I was to zoom in on this area here, you can see that there's a small channel or a step change. What I'm going to do is go to my profile tool, zoom in, draw a profile across this surface. And although the profile looks like there's not a lot happening, if we were to draw down the scale, we can see this step change or this channel. If I go to my single step now and create a step, you can see that that specific step in this area is 9.2 microns. Okay? So that was a very quick overview of how we would use interferometry on the Sensofar, and also the reasons as to why we would use those techniques. So now we're going to focus on confocal scanning. So confocal offers the best lateral resolution on the Sensofar system. So what we're going to do is we're going to take an electronic sample, we're going to place it onto the machine, and what I'm going to do is run you through the principle of how we would change technology and also measure from a starting sort of scratch point. So the first thing to note is on our technology summary, now we're looking at the middle column. So you're starting to see that confocal is probably the most versatile measurement technique. We're good at measuring rough samples. It's okay at measuring the smooth samples. On a micro scale feature, it's brilliant. Nanoscale features, it's not quite as optimal as using an interferometry technique. However, we can measure to relatively high slopes. We can also measure thickness measurements using the confocal technique. So if we were to go to the way that the Sensofar uses confocal, it's got a very slight change in the way that traditional systems will measure. So if you look on the left-hand side image, there's the laser scanning confocal. So effectively what this is doing is it's taking its points periodically, so we're snaking across the surface to obtain the map of the surface, whereas we're using a microdisplay confocal. So what we're doing is in one hit, we're taking all of that surface sort of topography. So when we're scanning, we're going to take data much faster. Confocal has the best lateral resolution, as I touched on, but this sort of confirms that data set, and we're able to measure to 140 nanometers in our X and Y planes. Now that is dependent on the objective that you use, so the one sort of downside as such to confocal is that we're dependent on the numerical aperture of the objective. So the numerical aperture will dictate the resolution. So if we were to have a higher resolution objective, we'll take a smaller field of view, but we'll be able to get a better lateral resolution. So they sort of sway on how much data you need versus the accuracy. So we'll jump onto the system now. So what I'm going to do is place the sample onto the bed, and we're going to swap over to our 20x objective, and I'm just going to move the system over to our sample. So I will go to the software, and I will use the tools that we have available to go and find the surface. So what I'm looking for now is where the surface of the material is. Once we've found that, we can now start to take our scans. So the first click I've done here is related to the lighting conditions. So that's automatically changing the light to the best or the most appropriate. I'm now going to set myself a Z0 position. So I'm going to start my scan in the highest Z positive. So I'll set myself the reference here. What that's done is it's over at my reference, my Z position. I'm now going to travel down until I've gone all the way through the focus. And you can see that I've travelled 164 microns. So we'll start by measuring over in our confocal, and I'm going to travel 150 just to make sure that I cover the full range. Travel back to my Z0 position. I'm just going to double check our lighting. Back to here and click acquire. So from here we're working in our confocal technique, and we've taken a scan over that whole surface. We've travelled 165 microns, and we've taken 167 planes. So we've scanned that, we've got the plane data here. So as you can see, we've got the data, some data on the edges, but there's a drop off in relation to where the slopes are. So if we reduce that leveling, you can see the effect that the slope has on the information obtained. Now if we were to look at the width of this slot, what we could do is go to our profile, snip across, and you can see that it's quite difficult to define where the width is here. So what we're going to do is we're going to set a point on the edge of this data set, which you can see is correct on this sense, ever so slightly to the right. That's the end of our data here, and on the right here you can see that it's the end of our data set here. What we can do is take the horizontal position from this point here to this point here, which is a 91.6 micron width. Okay? So when we were to look at this sample here, where the material is sloping off to a higher degree than we're capable of measuring on this relatively smooth sample, we'll have a maximum capability to measure to 70 degrees. So when we flip over to our focus variation, you'll see the difference in this data set when we use focus variation compared to confocal. And that's a very quick overview as to why we would use confocal scanning. So now we're going to be taking a look at focus variation. So focus variation is another technology that we can use on the Sensofar. And the main benefit to using focus variation is that we can measure high slopes up to 86 degrees on surfaces. So what we're going to run through in this short video is the scan of our previous sample. So where we had the channel on the component, what we're going to do is measure that using focus variation and then just do a comparison of the data sets. So you'll be able to see the differences and the sort of additional data that we can measure on focus variation compared to confocal. And then we're going to place another sample onto the machine and run you through the process of measuring an additive surface, because you can really obtain a lot of data on this kind of surface using the focus variation tool. Okay, so referring to our technology summary, we can see that we're now looking at focus variation, which is on the left-hand side. So it's very good for rough samples, not so good for smooth samples. It's okay for measuring the micro scale features, but not quite down to the nanoscale features. And that's because we have a limited X, Y, Z resolution on the focus variation setup. We have a high local slopes, so we're very good at measuring sloped features, and we can't do thickness measurements using focus variation. So what we're going to do now is swap over to the Sensofar software, and we're going to take a scan. So I'm going to swap over from confocal, and we're going to go to focus variation. So I'm now in the focus variation tool here. I'm going to go to my HDR focus variation, and what I'm going to do is just set my lighting. So I'm just going to change the lighting ever so slightly. We're going to run the same measurement parameters and take a scan of the surface. So I've got our previous scan data set, and I've also got the latest scan data set. And what we're going to do is just do a very quick comparison just to see the differences in the amount of information we get. So if I load up my confocal data set, we can see the differences between the amount of points in the channel compared to focus variation. So we're getting very little data on the bottom of this channel, whereas using focus variation, we're depicting a lot more of that information. So that's one of the real benefits to using focus variation compared to confocal in this application. So now what we're going to do is we're going to go back to our focus variation. We're going to measure a sample that has got a textured surface. So I'm going to place that onto the bed, and I'm just going to go and find the sample on the system. I'm just going to track this up. Just need to find the material. So we can see here we've got a visual of the texture of the surface. So what I'm going to do is to just set my lighting slightly less, and we're just going to take one sample, but this texture is going to be much more coarse. So the top of our sample is starting around this area. We're going to drop down by the amount where we've passed through it. So if I just come up to the bottom, just to about this area here. So we've traveled 300 microns. So what I'm going to do is to just travel 400 just to be safe. So I'll come back up to my Z0 position. We're just going to click acquire. So from here, we're going to be measuring using the focus variation setup. You can see we're slightly oversaturated on the light. So what we're going to do is just tweak that down ever so slightly. So I'm going to stop that scan. So it's nice and easy to show you how we stop a scan. So I've just clicked the escape button, and I'm just going to reduce my lighting down to around 4% and click acquire again. You can see now we've got a lot less saturation on the image, so we should get a nice scan on this data. So we've taken 417 planes over a 415 micron area, so we're effectively taking one plane every micron. And from this data set, we should see a nice textured point cloud that we'd be able to go and depict those step heights or those roughnesses. Now, focus variation and confocal, depending on the specifics of the roughness, we're using for a lot of clients that we have within the additive sector. So you can see here we've got a very nice data set that's got all of the sintered and non-sintered materials, as well as when we rotate this round now, you can see that we're picking up some data on these slopes, but not all of them, because some of them are going to surpass that 86 degree limit that we have. So if we wanted to go and look at the roughness values, these have already been calculated in the top right corner, but what I want to do is to understand the step height of one of these unsintered sets of material. So I'm just going to draw my profile across and click step height, and you can see that that's 147.2 microns tall. Okay, so it gives a very quick overview of how easy the software is to use, how easy the system is to use, and the different benefits between confocal, interferometry, and focus variation. So now we're going to take a look at spectroscopic reflectometry. So unfortunately I haven't got a sample to demonstrate on this technology, but I can run through the principles of how it's done. So within the software, what we're going to take a look at is we'll be using an interferometry lens, and we'll be measuring a reference sample. So this is a sample that we know the material structure for, and also the reflective properties. So reflective index and all of those kind of information. So from there we would take a single point, so we can range the spot size point from 3.5 microns to 40 microns, and we'll be taking a specific position and effectively calculating that thin film thickness. The thin film measurement, as I'd prefer to call this because the other way is a mouthful, we can measure between 50 nanometers and 1.5 microns, and the acquisition for that is less than 5 seconds. So it's a nice quick measurement once you're all set up and running. So if anyone's got any further questions on that, or has examples or applications specific to it, we'd be more than happy to run through the principle of that measurement. We tend to find that applications for us lead down the consumer electronics route, and also some automotive applications specifically relating to sort of the EV world as such now. So it's a very quick overview, but if anyone needs any more information, then please don't hesitate to get in touch. So lastly, we're going to take a look at Sensor Pro. So Sensor Pro is a Sensofar software. I would deem it to be the most powerful element to using a Sensofar S neox, because we can create specific scripts or routines to be able to solve the really challenging application problems that you may have. So within the software there's different utilities. So if I was to go onto our drop down here, we can see, if I close this window here a second, we can see all of the different types of utilities that are automatically already programmed into the system. So one of the most commonly used is blobs. So what I'm going to do is select our blobs function. If I go into our files, and I'll go to demo files. So what I've done is on our additive sample, I've taken 3 measurements. What I'm going to do is load those 3 Plux files in. So the Plux file is the point cloud data set from SensorView. And what I can do is click Analyze. So I'm not having to do any manual interaction here, and we can automate the input of the data and the output of the data, or the export as such. But it's automatically going in, it's reviewing the point clouds, and it's outputting me specific data that I've asked for in the blobs utility. So on the right hand side, you can see we've got all of our filtering setups. We're running a Gaussian filter, and on the first scan it's already completed. It's giving us all of the individual step changes. It's giving us a map of the position of them in the X and Y, as well as characterizing them by a number. Now the numbers link into this graph that we see here. So it's now completed all 3 of those, so we can look into the individuals or the sampling or the multiple groups. And if I was to go to view reports, you can see we've got all of the information related to each individual blob that's on this additive surface. So if we were to run through the same principle again, looking at roughness, so I can go to here, we can go to surface roughness. So if I was to go to texture, we will do a surface texture, and I'll click apply, and now I'll click analyze. And now what that's going to do is it's going to rerun the surface parameters for these components. So if I go to view report now, we've got all of our surface data. So it's a very powerful tool to be able to measure multiple samples and different areas of samples to still automatically output data. So that was a very quick overview of Sensor Pro. Hopefully you can see how powerful the software is for outputting data automatically in a CSV format. So now we're going to move on to our Q&A session. So thank you very much for watching, and we'll speak to you shortly.